So the topic this week is mirror descent. It is a version of projected gradient descent that respects or is tailored to the geometry of the feasible set. And as we'll see, it can be much faster than projected gradient descent. And the math here is also more intricate and for the nerds among you, cooler in some sense than the math that we've seen thus far. But this also means that some of the calculations are a lot more intricate, and so pay a lot more attention to following them in the references. Okay, so if you recall all the way back to the unit on gradient descent, we developed this majorization and minimization view of gradient descent. In particular, gradient descent with an appropriately chosen step length is a majorization minimization algorithm, meaning that each step it constructs this upper bound of the actual cost function, and then it minimizes the upper bound. Now, this upper bound has the property that it is sharp, it is tight at the iterate at which the bound is constructed. So let's say you're at iterate xt, you're going to construct this upper bound, we'll call it f tilde of t, and f tilde of t would agree with the actual objective function f at xt. Everywhere else it's an upper bound, okay? And you can see from the fact that you're repeatedly minimizing upper bounds that each time you are driving the objective value lower. Now, it turns out that projected gradient descent has a very similar interpretation. It is almost exact. It constructs actually the same upper bound as gradient descent. The only difference here is that instead of minimizing over the full decision space, all of Rd, we are going to minimize over just the feasible set. Okay, minimize or argument over x in script c. Okay, the f tilde t, this model function, is exactly the same as gradient descent. So it automatically has this upper bound property if the step length is small enough, and it also has the sharpness property. So in particular, f tilde of t at xt is exactly f of xt. Okay. Now, what this shows, again, it immediately implies that projected gradient descent is a descent method. Okay. But this is actually kind of a tangent. What we're going to use this majorization minimization approach of projected gradient descent to derive a better version of PGD that is suited to certain very special constraint sets. Okay, these are in particular constraint sets that have some type of very nice geometry to them. We'll see exactly what these are in a little bit. Okay, so let's take a closer look at this quadratic upper bound that is used in both gradient descent and projected gradient descent. So I have dropped all the constant terms. So you're going to end up minimizing this upper bound in x. So any of the terms that don't depend on x, you can just kind of forget about. We just want to look at the material quantities in this upper bound. And so the material quantities you recognize are first this quadratic proximity term. We call it a proximity term because it's basically capturing the closeness of x, which is your optimization variable in this upper bound, and xt, which is the current iterate. There's also a linear term, which is an inner product with the gradient or a subgradient at the current iterate. This is, in some sense, if you look at this linear term, this is the way in which the cost function enters this upper bound. Okay. In some sense, this is the correct upper bound to use generically, because if you recall in a Taylor expansion, if you expand it to first order, which is, so you would get this linear term that appears in this f tilde of t, this objective function for the PGD update, this model function that you're minimizing to carry out the PGD update. This Taylor expansion has an error that is roughly proportional to the square of the distance between x and x sub t, your new trial iterate, if you will, and the current iterate x sub t. So by sort of penalizing the quadratic distance between x and x sub t, you are in some sense you're trying to minimize the Taylor approximation plus the Taylor approximation error. So you're trying to minimize this type of conservative Taylor approximation to the cost function. Okay. Now, generally, this is a good idea, but what happens if your feasible set is something special? Well, say your feasible set, for example, let's say is the classic example of this, your feasible set is the probability simplex. Okay, so you're minimizing over probability vectors. These are vectors that are entry-wise non-negative and whose entries all sum to 1. Okay. Well, so for this probability simplex, it actually has a slightly different geometry. Like you don't usually use the Euclidean distance to measure the difference between probability vectors. You use, maybe entropy, maybe one of the F divergences, but the point is you don't really use Euclidean distance. I mean, you can. So in statistics, what we actually often do is we use Euclidean distance between the square root of the densities to measure differences between probability distributions. But you don't use Euclidean distance just straight up on the densities, which would be the analog of using Euclidean distance to measure the distance between probability vectors. That would be the analog here. Okay, so for these types of domains, for these types of feasible sets, you could presumably try to bake in the geometry of the feasible set into the PGD update rule by swapping out this proximity term for a proximity term that reflects the geometry of the feasible set. And this is exactly what is done in mirror descent. So this is the probability simplex example that I alluded to earlier. So on a probability simplex, you might want to use a different notion of distance, a notion of distance that's specifically tailored to probability vectors, or more generally, probability distributions. I mean, here are some examples. You can use KL distance. You can use Hellinger distance. This is actually, Hellinger distance is basically, L2 distance, but between the square root of the probability vectors instead of the probability vectors themselves. Or TV distance, also known as L1 distance. But you can use any, there are a lot of other distances that you may want to use. There are many divergences between probability distributions. But the point is you don't want to use the Euclidean distance. Okay, so we motivated this video with this example about the probability simplex, but let's take a step back now and try and paint a more general picture of what's going on. So in general, in this video of mirror descent, we're going to consider a general class of proximity terms called Bregman divergences. Now, these are, we say that these proximity terms are measuring distance, but they're technically not a norm, not a distance function in the strict mathematical sense of the term, because they don't satisfy, for example, they're not symmetric in their two arguments. But they do have a lot of nice properties that are very useful in optimization, and we will see some of them later. But for now, let's first define what a Bregman divergence is. So every Bregman divergence is induced by a differentiable and strictly convex function. Okay, you give me a differentiable and strictly convex function, I will cook for you a Bregman divergence according to a certain formula, which we'll see in a little bit. So given a function phi, this differentiable and strictly convex function, maybe just call it a base function if you will, how do I get the Bregman divergence? Well, the Bregman divergence induced by this base function between 2 points x and y, let's say, okay, is the following quantity. First, you go to this base function and you evaluate it at one of the points. So you get phi of x, okay? And then what you do is you go to the point y and you construct the first order Taylor expansion of this function phi at y, okay? Now, armed with this first order Taylor expansion, you are going to evaluate this first order Taylor expansion at the original point at x. Now, because the function is strictly convex, the first order Taylor expansion will always sit underneath the function itself. So there's going to be a difference between the function value, the value of the actual function at x, so var phi of x, and the value of the Taylor approximation at x. Right? This is the Taylor approximation taken at the other point y. Okay, and there's going to be a difference between these two, and this difference is the Bregman divergence. Okay. So, in summary, Bregman divergence is just the difference between var phi and its first order Taylor expansion. Okay, and you're constructing the Taylor expansion at one point and then evaluating this difference at the other point. That's basically what a Bregman divergence is. Okay. Now, it's very important to note that the Bregman divergence is convex in its first argument. So this is the point at which you're doing the evaluating. Okay, not the point at which you're constructing the first order Taylor expansion. Now, it's doesn't have to be convex in the other argument, right? So it's very easy to see why it's convex in the first argument, because in this first argument, what is it? It's basically a convex function, right, plus a linear function, right, in x. Now in y, it's it's a negative convex function. It's a concave function, right? And then plus this weird term that we don't really know what it is. It's not linear because the derivative depends on y. And so Bregman divergences are basically very easy to deal with in terms of its first argument. And as we'll see in the analysis, we will generally only always deal with the first argument of the Bregman divergence. Okay, so that was the definition of a Bregman divergence. Let's see some examples. So our first example is actually something that you're quite familiar with. It's the squared Mahalanobis distance, or the squared proximity distance, okay? This quantity is not a norm. Its square root is a norm. In fact, the square root is just a Euclidean norm, or weighted Euclidean norm. But the function itself, right, without the square root, the squared Euclidean distance, if you will, it is not a norm. In particular, it does not satisfy triangle inequality. So it's not a proper notion of distance. However, it is a Bregman divergence. It is the Bregman divergence induced by the quadratic function. Okay? And you can check this. This is quite easy to check. Just sort of plug in a definition. Okay, so now let's go back to the KL divergence, which is a notion of distance between probability distributions that we've seen before. Now, it's technically, again, it's called a divergence because it's not a strict notion of distance, again, because it's not symmetric. Right. The KL divergence between x and y is not the same as the KL divergence between y and x. However, it is a Bregman divergence. It is the Bregman divergence induced by the negative entropy function on the non-negative orthot. So this is also quite easy to check. You just sort of plug in the definition. However, what I want to point out is that if you look at the KL divergence this way, as a Bregman divergence, you get a very natural extension of it to beyond the probability simplex. So these are vectors or points whose entries are non-negative, but they don't necessarily sum to 1. Okay, and this is called the extended KL divergence, and it's very easy to see what it is on the by taking this Bregman view. So if I on the simplex, right, you see that these two terms that pop off beyond the usual KL divergence, they would cancel each other out because everything on the simplex sums to 1. Right? But off the simplex, these two terms start to matter. Okay, so we've seen two examples. These are in some sense the ones that are easy to derive. There is a whole family of examples, and I've given you a table here, but this table is again hardly exhaustive. So there are a lot of Bregman divergences. They're all suitable for different feasible sets, different domains. And so when you are faced with an optimization problem with one of these special domains, then you should use the appropriate Bregman divergence. Okay, so we've seen all these Bregman divergences, but at the end of the day, the correct way to understand these Bregman divergences is that they're in some sense all weighted squared Euclidean distances, or weighted squared Mahalanobis distances. How do you see this? Well, you just take the definition of a Bregman divergence, and then you Taylor expand the difference between the two function values of R phi, and you Taylor expand it to second order. You will notice that the first order term, if you expand it at the correct point, so if you expand the second argument, will cancel out with the linear term that appears in the definition of the Bregman divergence, and all you're left with is the quadratic term. Okay, and it is this quadratic term that the Bregman divergence, at least when the points in the argument are close, is approximating. Okay, so it's basically some type of squared Euclidean distance, squared Mahalanobis distance. So a couple properties are easy to see. So first is non-negative, and this is just a consequence of the strict convexity of phi. Okay, if phi is strictly convex, then there's always going to be a positive gap between the Taylor expansion of the function and the first order Taylor expansion of the function and the function itself. It's also easy to see that the Bregman divergence is convex in the first argument because it's a strictly convex function plus a linear term. So linear terms never alter the convexity of functions. Finally, Bregman divergences are generally asymmetric. So generally, if I look at the Bregman divergence between x and y and x, they're not the same. However, the fact that it's a locally quadratic distance function, which is symmetric, suggests that even though the Bregman divergence may not be exactly symmetric, it's approximately symmetric if the 2 points are close. Okay, so They're not, yes, technically it is a quadratic, but it behaves a lot like a quadratic function in a small neighborhood. So a couple other properties of Bregman divergences. The first is linearity with respect to the base function, this function phi, which we're using to induce the Bregman divergence. And this is really very easy to see just by checking the definition. You just plug phi plus lambda phi 2, phi 1 plus lambda phi 2 into the definition, and just notice that all the terms you can regroup the terms basically into the Bregman divergence induced by phi 1 and lambda times the Bregman divergence induced by phi 2. The other property is invariance, so linear shifts. Again, this is not hard to see. You just plug. So what it says is that if I take the space function and I add a linear term to it, so a term that's the form, a inner product with x plus b, this type of an affine term, then it doesn't change the Bregman divergence. And the way that you see this is you just plug this linear term in and see that it just cancels out in the definition of the Bregman divergence. The last thing, which is actually going to be quite useful, is that the gradient of the Bregman divergence with respect to the first argument, we're almost always differentiate with respect to the first argument because it's the argument that's convex and therefore the argument that it's possible to optimize it. So the gradient of the Bregman divergence with respect to the first argument, this is going to be the difference of the gradients of the base function between the first argument and at the second argument. Okay. This is, again, a property that's quite important. We'll use it quite a bit. Okay, so we get to our first, maybe slightly more non-trivial property of Bregman divergence, and this is known as what's called the three-point lemma. Okay, you can think about it as a generalization of the law of cosines. Okay, the way that you see this is that, so recall, if I pick. So the way to see all this stuff is to think about the Bregman divergence induced by the function. Var phi is just 1/2 the Euclidean norm of x squared, okay? Or 1/2 phi of x is 1/2 x transpose x. So for this Bregman divergence, the gradient of phi is just the function, is just the argument to the function itself, right? The gradient of 1/2 x transpose x is just x. And so if you think about specialize the definition of the Bregman divergence to this particular base function, you will see that you exactly get the law of cosine. So all this, Bregman divergence between x and y, this just becomes x minus y Euclidean norm squared. Okay, and then remember the gradient of phi, right? This is just the argument in this case. So the gradient of phi at y is just y, and so the gradient of phi at z is just z. And so if you just plug in all the terms, you get exactly the law of cosines. Okay, this is worked out in generality for you in the references, but essentially this is the Bregman divergence version of the law of cosines. Okay, so given that a Bregman divergence is some notion of distance, right? It's not a proper distance function per se because it doesn't satisfy triangle inequality, is not symmetric, yada yada yada. But you can use it to if it intuitively encodes some notion of distance, then you can use it to define projections by simply asking for the minimum distance points. And so if you do this, then you get what's called a Bregman projection, and it's defined exactly what you think it, in the way that you think it is. So if you give me a point x, I want to project x onto, let's say, a set script C, then the projection is simply the closest point in C to x. So this is the projection of x onto C. This is the closest point to x in C, where close is defined in terms of the Bregman distance. Now, it is very important, remember, because Bregman distances are not symmetric, that which argument you are going to put the projected point and which argument you're going to put the original point in. Now, because the projection is defined as an optimization problem, and you always want to solve convex optimization problems, so the decision variable in this optimization problem, in other words, the point that is you're sort of looking for in the convex set, that's this is not the point that's being projected, right? This is the projection. This is going to be the first argument of the Bregman projection this is going to be the first argument of the Bregman divergence, because remember, the Bregman divergence is convex in its first argument. It's not convex, it may not be convex in the second argument, but it is convex in the first argument, okay? Of course, there are instances where the Bregman divergence is convex in the second argument. In particular, instances where it's symmetric. So, for example, if I pick the base function to be 1/2 x transpose x, then it leads to a symmetric Bregman divergence. The Bregman divergence here is just a squared Euclidean distance, and so then it's convex in both arguments. But generally, Bregman divergences are not. Think, for example, the KL divergence. Okay. The key here again is that the point that you're being projected, that the point that you are projecting, so not the projection, the point that you are starting with, this is going to go in the second argument of the Bregman divergence in the optimization problem that is defining the Bregman projection. Okay. Finally, the Bregman projection satisfies again a version of the projection theorem. Okay, and this is something that is quite easy to see. You just write down the optimality condition of the optimization problem that defines the Bregman projection. The particular optimality condition that you write down here would be that if I look at the gradient, the directional derivative of the objective function, any feasible direction, has to be non-negative. Right? This is the optimality condition for a minimization problem. It means that in any direction that's feasible, if I move a little bit, I always increase the objective value, locally at least. Right? And so this condition is exactly the statement of the Bregman projection theorem. Okay, so you can also cook up a Bregman Pythagorean theorem, except here it's not an equality, it's an inequality. The proof of this is given to you in the references, but the key difference again is that this is an inequality. But if you were to pick the base function to be 1/2 x transpose x, then this does become an equality, and you just recover the usual Euclidean Pythagorean theorem. Okay. Okay, so we spent all this time setting up all the fundamentals, all the basics, all the definitions. What was it good for? So we finally get to the mirror descent algorithm, which is the algorithm that we're going to be talking about in this video. So as I alluded to earlier, it looks a lot like projected gradient descent. The only thing that you did was you looked at the projected gradient descent update rule, or I should say you look at the majorization minimization sort of view of projected gradient descent, and you inside the majorization function, you replace the quadratic proximity term with a Bregman divergence. That is literally the only thing that you did. Okay. Now the key is so. Actually, in some sense, this is a more general algorithm than projected gradient descent because, as we saw earlier, the quadratic proximity term is a Bregman divergence. Is the Bregman divergence induced by var phi of x is 1/2 x transpose x. Okay, and so the question at this point becomes, since you have all these this more general view on things, how do you pick a good proximity term? Okay. So there are three main concerns here when you're picking a Bregman divergence, because in some sense this proximity term is sort of defining the algorithm for you, right? Once you pick a proximity term, you have a well-defined algorithm. So it depends on three things. First is the local curvature of the function f. Okay, so earlier we saw that Newton's method is an instance of Bregman divergence, of mirror descent, where you picked a weighted quadratic function as your proximity, where you pick a weighted quadratic proximity term. So here, this proximity term was purely driven by considerations about the cost function. You're trying to approximate the cost function better. Okay. You could also pick the proximity term based on the choice of the feasible set. This is what is done in mirror descent on the probability simplex. This is known as the exponential gradient algorithm. We'll see that later. Here, so you only make this consideration based on the geometry of the feasible set. Finally, when you pick this Bregman divergence, you also need to project with respect to it. So you could pick it so that the projection is easy. Okay, this is a third consideration. Okay, so let's see some examples of Bregman divergences. So the first example that we see is Newton's method. This is actually, for those of you who've taken an optimization course before, Newton's method, its benefits are widely touted for unconstrained optimization. So here you see that it's actually an instance of a Bregman divergence. And in particular, the Bregman divergence that you pick is just a weighted squared Mahalanobis distance. Now this matrix of weights in the middle is chosen depending on the current Hessian of the objective function. So this is one of the examples of a mirror descent algorithm in which the Bregman divergence is chosen purely in order out of considerations for the cost function. Your goal is to sort of approximate the cost functions more closely by using a second order instead of the usual first order approximation. And this actually works really well locally. Okay, what is kind of surprising when you sort of think about Newton's method compared to, let's say, gradient descent, is there's always this folklore that Newton's method is so much faster. It's converges so much quicker. It's so much more efficient than gradient descent. Gradient descent tends to get stuck bouncing around all these steep valleys and so on and so forth. However, if the benefits of Newton's method, at least you cannot prove it theoretically. And here's what I mean. So Newton's method has this, for those of you who've taken an optimization class, maybe seen Newton's method and its convergence properties before, it has this property where it sort of converges, what they call superlinearly or quadratically. This is a rate of convergence that's very, very fast, and we've actually never seen any algorithms with this rate of convergence in the class before. But this property of Newton's method is only holds in a vicinity of the optimal point. So you have to first get yourself to within a small neighborhood of the optimum, and then it converges real fast. Okay, but if I look at the convergence behavior of Newton's method globally, so not locally, not the rate only after it gets really close to the optimal point, but its rate over the entire optimization process, then it's actually just linear. Yeah, it has a slightly better constant than the linear convergence of gradient descent, but it's still linear. It's the same convergence rate. And so this folklore that Newton's method is so much better than gradient descent, this is oftentimes not borne out in practice. It's especially damning because in statistical practice, you're oftentimes not interested in the super high fidelity solutions, and this is really where Newton's method shines, right? Like if I get close, and I want to get a super accurate solution, tolerance 10 to the minus 8, 10 to the minus 10. Newton's method will get there for you real fast compared to gradient descent. Gradient descent it will take much longer to make up the last few, to get you the correct last few decimal places because it doesn't have the superlinear property. But in statistics, you're not really looking for that highly accurate solution anyways, because you have to keep in mind at the end, the solution that you're getting for this optimization problem, it itself is an estimator. It itself is data dependent. So you get a fresh batch of data, you're going to get a different estimator anyways. So there's no point in solving this algorithm, this optimization problem to very, very high precision because there's some innate variability in the solution due to the randomness of the data. And so if you're just looking for a very coarse solution, gradient descent, hey, that works fine. Because up till, let's say 10 to the minus 2, Newton's method and gradient descent, they're all getting the same rate. Maybe Newton's method has a slightly better constant, but remember, gradient descent, each time you only have to evaluate the gradient. Newton's method, you have to not only evaluate the Hessian, you also have to possibly, if it's a high-dimensional problem, solve a very large linear system. So at the end of the day, gradient descent might actually be faster if you're just looking for a very coarse, medium quality solution. Okay, so recall there are two versions, there's sort of two equivalent ways to view projected gradient descent. So the first way, and this is the way that we actually first saw it, this is the way we saw last video, actually 2 videos ago, is what you did was you first took an unconstrained gradient step, and then you projected it back onto the feasible step. So there was this sort of, two-step process, right? So you generate this intermediate iterate, we call it, xt plus a half. This iterate, it's not necessarily feasible, but so to get the actual iterate that you want to be feasible, to get the xt plus 1, you took this xt plus a half, which is just xt plus a unconstrained gradient step, and you projected it back onto the feasible step, right? Okay, so we then saw that this algorithm is actually equivalent to, you can write it as a majorization minimization algorithm, where what you did was you actually used the local quadratic model that is used inside unconstrained gradient descent, and you simply, instead of minimizing it over in an unconstrained way, you minimize it over the feasible set. And this was also projected gradient descent. Okay, now for mirror descent, what we did was we started with the majorization minimization sort of approach, where we said that okay, you're taking an argmin of this model over the feasible set. This model was, very closely related to this quadratic model that we've been using in gradient descent and projected gradient descent. The only difference is that you took the quadratic proximity term and now you replaced it with a Bregman divergence. Right? Okay. So it turns out that mirror descent, you can also think about it in terms of this, in terms of a two-step procedure. And so what you do is you first take an unconstrained gradient step. So now recall the unconstrained gradient step. This is going all the way back to the first video, right? The unconstrained gradient step is itself the minimization of in this case, a quadratic function, right? And what you did was you took the first order approximation to the objective function and you tacked on this quadratic proximity term. If you do the same thing here, you replace the quadratic proximity term with your Bregman divergence, then you get the mirror descent analog of this unconstrained gradient step. Okay, and this gets you xt plus a half, just like in projected gradient descent. Now, this xt plus a half may not be feasible, so what you do is you take a projection back onto the feasible set. The only difference here is that this projection is now no longer with respect to the Euclidean norm. This is a Bregman projection. Okay, so in the first, let's say half, if you will, of this two-step view of mirror descent, you took a quote-unquote steepest descent step with respect to the Bregman divergence, with respect to the Bregman proximity term. Okay, and then in the second step, what you did was you took in order to make your iterate feasible again, you took a Bregman projection step. Okay, again, if you replace both the Bregman projection and the Bregman divergence with, let's say, just the square Mahalanobis distance, then you get back projected gradient descent. Okay. And the way you see this is actually very easy. You just you can compare optimality conditions. Okay, you just write out what the optimality condition is for the first argument, and then you write down the optimality condition of the projection, and then you just compare it to the optimality condition of mirror descent as defined by a single constraint minimization problem, and you see that they're exactly the same. Okay, so let's look at another example of mirror descent. This is probably the most prominent example. Newton's method is a big example, but it's not really. Some people don't consider it a real instance of mirror descent because the Bregman divergence term is sort of changing every iteration. So if you recall, in Newton's method, the Bregman divergence at each iteration is a squared Mahalanobis distance, where the matrix of weights in the middle is dependent on the Hessian of the cost function at the current iterate. So as my iterates change, this Hessian changes, which changes the Bregman divergence. So people don't consider this as a concrete instance of mirror descent because it's like you're always changing the Bregman divergence, and you're not technically supposed to do that. You're supposed to pick a Bregman divergence at the beginning and kind of stick with it. So exponentiated weights, for these people, this is the most prominent example of mirror descent. Don't get me wrong. This is itself it's a very prominent algorithm. So it shows up a lot when you. So this is basically mirror descent over the probability simplex. Okay. Now. So let's talk about the details of the algorithm first. So you're going to pick the KL divergence as the Bregman divergence, and if you work out what the mirror descent update rule is, you can actually do this in closed form. What you see is that this mirror descent update rule, first it's very nice because there's you can get it in closed form. You don't need to explicitly compute this projection, no optimization problem to solve, and you can see that how the closed form, this form of this mirror descent update, this exponential weight update, maintains feasibility. So first, in order to stay in the probability simplex, what do you need? Well, you need the entries of the vector to be non-negative, and you need all the entries to sum to 1. Okay, so how does it ensure that the entries are non-negative? Well, assuming that your current iterate x of t is in the probability simplex, so its entries are already non-negative. What you're going to do is you're going to multiply the update that's coming from the cost function. This is going to be in this vector g sub t, right? This is the subgradient of the cost function. You're going to multiply it by the step length, which is non-negative, and then you're going to exponentiate it. Okay. When you exponentiate, you turn any quantity into non-negative, and so if you multiply this exponentiated gradient, which is where it gets its name, with the current iterate, you're going to get another non-negative number. Now, after you do this set of numbers, these are the components of your new iterate, if you will, they no longer sum to 1 because again, they used to sum to 1, but now you've sort of scaled each entry independently. You have no idea what they sum to. So the exponential weights update then proceeds to normalize each entry by the sum of the entries. So this is how, so you see here explicitly that feasibility, at least with respect to the simplex, is being preserved. Now, why does this algorithm show up so much? Why is it so prominent? Because it's especially prominent in economics and game theory, because in economics and game theory, there's a very large sort of portion of it that is devoted to randomized strategies. Now, anytime you have, because pure or non-randomized strategies, sometimes if you restrict yourself to such strategies, oftentimes games don't have equilibria, which are sort of the end goal, the end state of games. Only if you consider randomized strategies do you have all these nice notions of equilibria, for example, Nash equilibria. And so when you look at randomized strategies, you're essentially sort of optimizing over probability distributions, right? These are probability distributions over the pure strategies. And so whenever you carry out this type of optimization, the exponential weights algorithm comes into play. Oftentimes you'll see this in the context of a min-max problem, like let's say a two-player zero-sum game. And so each side will be doing the min-max algorithm. So one side will be doing the exponential weights as a minimization algorithm, and the other side will be doing exponential weight, but the maximization version of it. And so this is why this algorithm shows up so much and why it's so prominent. Okay, so I stuck the slide in here because I think I couldn't really get away with not telling you why this algorithm is called mirror descent. But unfortunately, to fully understand why this algorithm is called mirror descent, it requires you to understand duality, which we haven't gotten to yet in this class. So we will sort of come back and discuss this topic, but for now, I want to just give you a taste of why this algorithm is called mirror descent. The mirror descent algorithm was derived by Nemirovsky and Yudin all the way back in the 80s, I believe in 1983. And the way they derived it is it's the exact same algorithm as I have presented to you. So if you run their algorithm and you run the algorithm that I'm telling you, you will get exactly the same iterates. It's just like, there's sort of, we already have two equivalent views of mirror descent. There's the first view where you do this constraint optimization, where you take the first order Taylor expansion of the cost function and you tag on this, Bregman divergence proximity term. That's the first view. And the second view is you do this unconstrained Bregman divergence, steepest descent step with respect to the Bregman divergence. And then you do a Bregman project. So this output of this step, this is the xt plus a half that we've seen. It may not be feasible because this is an unconstrained steepest descent step. Now you're going to project back onto the feasible set with a Bregman projection to ensure feasibility, right? This is this two-step view of mirror descent. And these two are equivalent algorithms. Now there's a third view of mirror descent that I haven't told you about. And this is the dual view of mirror descent. And this is what I'm going to try and allude to in this slide, but you can't really fully understand it until you understand duality. So how does this work? So we're going to define a alternate series of quantities, and these will be quote-unquote dual quantities, okay? They're dual in the sense that so for those of you who know a little bit of functional analysis, if you have a vector space, the dual of the vector space is the set of all linear functionals on the vector space. So, for example, in functional analysis, you would distinguish between the function, right, and its gradient. So the gradient of a function, this would be a linear functional, is a member of the dual space, okay, versus the domain of the function. This will be in some sense the quote-unquote primal space or the original space. So what I'm going to do is I'm going to define a sequence of quantities that these are quantities in the dual space because, as you will see, they are in the image of the gradient map. Okay, so in particular, I'm going to define the series of quantities, these y sub t's. Okay, and the mapping between the y sub t's and the y sub t and the x sub t's is you'll sort of see what's going on. So first, I'm going to define this. We call this intermediate iterate. This iterate that I get after I do steepest descent with respect to the Bregman divergence. This xt plus a half. Okay, this may not be feasible, but I should say this whole view that I'm presenting here is simplified. I'm taking the view that you actually have no, so the feasible set is not it's just the whole RD. And so what you actually see is that if I define this, if I take this xt plus a half, this intermediate iterate, and I'm going to pass it through the gradient map, okay? So now it's something in the dual space because I passed it through the gradient map. And I'm going to call this quantity yt plus 1, okay? So what you will see is that yt plus 1, right, by the first order optimality conditions of this steepest descent step with respect to the Bregman divergence satisfies this equation. Yt plus 1 is equal to the gradient of phi at xt minus eta t gt. Gt, remember, is the gradient of the cost function. Okay, so, and this is, no, everything is being done in the dual space. You have yt plus 1 is equal to the gradient, right, of var phi at xt, because it's the gradient, it's in the dual space, and gt itself is the gradient of the cost function, so it's also in the dual space. Eta t is a scalar, right, so you're doing some linear combinations in the dual space. Okay, so now, so this is what yt plus 1 is, and now what you do is you go back to the primal space and you look at the optimality conditions of the Bregman projection. Well, in this case, there's sort of nothing to do here. So if I look at the Bregman projection step, it's really just the identity step. And if you again recall the definition of yt plus 1 as the subgradient of phi at xt plus a half, then you realize that the optimality conditions of this Bregman projection step tells you that yt plus 1 is exactly equal to is also equal in this case to the subgradient of phi evaluated at xt plus 1. Okay, and so with these sort of two relations in place, I can kind of allude to why mirror descent is called a mirror descent. So imagine you have these two sequence of iterates. Okay, you have these xt's and you have the yt's. The xt's are in the primal space. The yt's are sort of the mirrors, okay, the corresponding entries in the dual space, okay, and they're related by a gradient map because, again, once I take points in the primal space and I evaluate the gradient, I get some point in the dual space, right? The gradient map is also maps points in the original, the primal space to the dual space. This gradient map that relates these two sequences of points is precisely the gradient map of this base function that you're using in the Bregman divergence, this var phi. Okay, so you can take xt, and you're going to do map it to the dual space. You get this yt's, and then in the dual space, right, what you do is you actually just you're doing plain vanilla gradient descent. You're just taking yt and you're adding eta t gt. Right, this is the step in the dual space, right? And then what you do is once you add this step, you get yt plus 1, you are going to map it back to xt plus 1, okay? And so there is this mirrored sequence of iterates in the dual space, where in dual space it's basically just gradient descent, okay? But when you mirror it back into the primal space, you get this very complicated sequence of iterates. This is what is meant by mirror descent is gradient descent in dual space. This is the dual sort of perspective of mirror descent. This is the original way that Nemrogowski and Yudin, who sort of first derived mirror descent, how they saw the algorithm. But unfortunately, we cannot fully appreciate it here. But in a few weeks, you will be able to. But this is just a taste. Okay, so we spent a lot of time talking about mirror descent. Now let's look at some of its convergence properties. So the types of optimization problem we're going to solve here, these are non-smooth optimization problems. So it's the same kind of optimization problems that you would solve with the subgradient method. But here, instead of the subgradient method, you're going to use mirror descent. So your objective function, again, is convex, and you're going to assume that it's L Lipschitz with respect to a norm that is, we're going to denote as norm sub star. So you remember in the subgradient lecture, we saw this concept of dual norms, okay? So the convergence result would be stated in a pair of such norms, so a norm and its dual, okay? And right now, what you want is you want the function to be L Lipschitz with respect to its dual, okay? This actually all sort of makes sense in light of the the primal and dual business that we talked about on the previous slide. So you always have if you're going to distinguish between the primal and the dual space, then you're always going to be measuring things in the dual space with the dual norm. So in your primal space, you got your normal norm. Then the correct norm, in some sense, to use in the dual space, if you're using this primal norm in the primal space, is to use the dual norm of whatever this norm that you're using is called the primal norm. Now, if the norm is the Euclidean norm, then the Euclidean norm is in some sense is self-dual. So the dual of the Euclidean norm is the Euclidean norm. And so in gradient descent, you don't have this disparity. But when you look at mirror descent, you need to sort of maintain this separate geometries in the primal and dual space. This is why you see all these primal and dual norms sort of popping up. But anyway, so the correct norm to measure so if I have a function, it's L Lipschitz. That just means that its gradient is going to be you're going to derive some bound on the gradient, and so the correct norm, the gradient, remember again, is in the dual space, and so the correct norm to look at the size of the gradient is the dual norm. That's what I mean by L Lipschitz with respect to the dual norm. Okay, the feasible set is just closed convex set. This is the same, and now the cost function we're going to be strongly convex with respect to the primal norm. Okay, and this is because you're using this norm to measure distances in the primal space, right? In X space, in the iterates, and so in the iterates, you're going to use the primal norm. Okay, no, I'm saying the primal norm, the dual norm, but these things really exist as pairs. You give me any norm, I can tell you what its dual norm is. The definition is sort of we saw in the previous video on subgradient descent, and so this convergence result is basically saying when you measure whatever norm you use to measure the L Lipschitz as a function, you have to use its dual norm to measure the strong convexity. Okay, so and again, remember the dual of the dual norm is subject to some regularity condition. Is just the primal norm. So you can speak of the dual of duals. This is also why it's called the dual, because the dual of the dual is just the primal. Okay, so this is how the setup is going. Aside from this, slightly strange geometry where you have to differentiate between the geometry of the primal and the geometry of the dual space, everything else is very standard. Okay, so here we have the convergence result. It is actually very similar to the convergence result that you saw for subgradient descent. Rates are quite similar. So if you just look at this result, you immediately get a couple things. So the first is that it suggests the diminishing step size 1 over root t. Okay, the reason is it's a very sort of efficient. So you want to make the sequence of step size as big as possible, right? But at the same time, you don't want the numerator, which is the sum of the sequence of step size squares, to blow up. So the easiest way you can sort of do this is you want to make the step size as big as possible without it blowing up. So kind of right on the boundary is this 1 over t sequence of step size. Sorry, 1 over root t sequence of step size, because the sum of squares is log t, right? It goes slower than any polynomial, so it's like just barely blowing up. But fortunately, the numerator is going to be it's going to be square root of t, and square root of t. I guess the denominator is going to be 1 over is square root of t. So log t over root t, this still goes to 0, and so you're sort of still okay. And if you ignore the fact that basically log t grows super slowly, so it's basically 1 over root t convergence rate. So this is again comparable to subgradient descent. And the other thing is I've sort of stated again this convergence result in terms of this average iterate, but again, any result that, as long as f is convex, any result for the average iterate is also going to hold for the best iterate observed thus far. And so we're going to state the result for the average iterate, but just be aware that just like all the results before for the average iterates, you can translate it into the best iterates on the sequence. Okay, so this is the optimal rate that I sort of alluded to on the last slide. Here I've sort of written out the constants for you, but basically it's a 1 over root t rate, and you see that 1 over root t causes the sum of the square of the step lengths in the numerator to be roughly of the order log t, right? And the sum of the iterates itself, no square, to be roughly root t, and so you get a log t over root t rate. It's possible to remove the log t factor, but I mean, who really cares? Okay, so at this point, you want to ask yourself, so we went through all this hoopla, define, this primal and dual spaces, we cook up this Bregman divergence, and we cook up this algorithm called mirror descent. And, so far we see, okay, it generalizes projected gradient descent, but why on earth would you go through this exercise? What are the benefits? Well, so we'll see that you can really get some speed ups out of mirror descent. But before sort of I dive in and tell you, how great mirror descent is, I just want to say that mirror descent is kind of a niche algorithm. Okay, so in cases where it works really well. You'll see it in a few slides. But the places where you kind of can finagle things to get it to work is not that common. So you can only probably do it in like very stylized problems. And so it's algorithm that's sort of good for proving bounds. Like if you want to show that it's possible to do some tasks, and you sort of boil the task down to solve an optimization problem, and then you really want to really improve your result on how quickly you can solve this algorithm, then mirror descent is like a perfect algorithm for this kind of thing. This is also why it appears in like game theory and econ, because what you want to show is that the game is solvable in polynomial time. Let's say and you want to drive the order of the polynomial as small as possible. But in terms of practice, it's not unless you have a situation where it sort of really fits nicely with mirror descent, it's not worth it to try and get mirror descent to work. I mean, regular gradient descent is probably just as fine. That being said, when mirror descent works, it bombs. So here's an example. Okay, so you're going to do optimization on the unit simplex, okay? On the probability simplex. And you're going to use gradient descent. So gradient descent, remember, is projected gradient descent. Projected gradient descent, if you recall, is an instance of mirror descent, right? Where you take the Bregman divergence to be the squared Euclidean distance. So if you just run through this plug and chug through the previous bound, what you see is that you get a 1 over root t rate. Okay. Keep this in mind because we're going to compare with mirror descent, where you use the KL divergence at the Bregman divergence, which is in some sense the correct one to use here. Because again, you're optimizing on the probability simplex, you want to use a divergence that reflects the geometry of the probability simplex. Okay, so now let's do mirror descent. So in order to do mirror descent, what we're going to use the KL divergence, and this is the divergence induced by the negative entropy function. Okay, so if you go back to the theorem, one of the stipulations of the theorem, the conditions, is that you need this var phi, right? This function that you're using to induce the Bregman divergence, the negative entropy function here. You need to be strongly convex with respect to some norm, right? And then you're going to require the cost function to be L Lipschitz with respect to the dual norm, right? Okay, so the correct norm to pick here turns out to be the L1 norm, because the negative entropy function is strongly convex with respect to the L1 norm. This is called Pinska's inequality. It's not entirely obvious, but it's true. And so once you pick these norms, you can sort of chug through just plug everything into the gradient descent the mirror descent theorem, and you get what seems like the same rate, right? It's again a log t over root t rate. Okay, so it doesn't look like we gain anything. Well, the devil here is in the constants. You recall, for the gradient descent rate, right? For the gradient descent convergence result, the constant in front, there was this Lipschitz constant of the cost function. And the Lipschitz constant in this case was taken with respect to the Euclidean norm, right? Because again, for that analysis, we were using 1/2 x transpose x as the base function to induce the Bregman divergence. And so that function is strongly convex with respect to the Euclidean norm. Versus for the mirror descent version, this exponential weights, if you will, version, we were using the L1 norm, right? Now, the L1 norm is in some sense, and this is what I keep saying what I mean by, it's tailored to the geometry of the set. So the if I look at the dual norm of these two norms, because that's what the Lipschitz constant is depending on, because the Lipschitz constant, again, is the Lipschitz constant of the function, right? And a bound on the Lipschitz constant is really a bound on the gradient of the function, or the subgradients of the function, and so subgradients, being in the dual space, are measured with the dual norm. Okay, so if I use the dual of the L1 norm, which is the L infinity norm, to measure the size of the gradients, generally the size of the gradients are the L infinity norm is smaller than the L2 norm, right? Which is what I would be using to measure the size of the gradients in the gradient descent analysis. Okay, so the gain here, right, is the gain of the difference between the L infinity norm and L2 norm. And this gain, right, can be up to root d, right? And so what this upshot is that if I have a problem and this problem is high dimensional, then mirror descent might converge much faster. Okay, and this gap increases as dimension grows. Now, this is very important because if you think back to my analogy earlier between gradient descent and Newton's method, which is why I brought it up earlier, and I said there's no real difference between gradient descent and Newton's method, right? I said that, yeah, in Newton's method, you get rid of depends on the condition number in front of the constant, but other than that, they're really the same, linear rate. Here, what you're seeing is a much bigger difference. Here, yes, it's in the constants again, but here the constants are dimension dependent. Right? So the difference here is a factor of square root of dimension, which is a much bigger deal than just getting rid of the condition number in Newton's method versus gradient descent. So the other way to think about it is that for this particular application, optimizing on the probability simplex, right, the difference, the improvement that mirror descent is over regular gradient descent is larger than the improvement that is typically perceived by people between gradient descent and Newton's method. It's more of an improvement here, okay? Because here, theoretically, it makes a huge difference. Okay, so theoretically it makes a huge difference. Does it make a difference empirically? Well, let's look at an example. I should be very clear. I stole this example from Stanford's EE 364B class, which is where I learned all this stuff. So you're getting it straight from the horse's mouth. So here's an example. It's a robust regression problem. You see this kind of thing actually in statistics in quantile regression, where so here what we're looking here you can think about as median regression, right? You're minimizing the L1 norm. If I were to weight both sides of the L1 norm in a very special way, then I can actually get the quantiles. And that would be quantile regression. Professor Shuming He in the department, he does a lot of quantile regression. Anyways, so when you do this type of quantile regression, at the end of the day, you end up to compute the actual estimator, you end up solving a linear regression problem. So this is the linear regression problem, and you see that here I've constrained the decision variables to be over the probability simplex. Okay, and I'm going to run projected subgradient descent and mirror descent, and this is the difference. Okay, so I generate some random data, and I plot the convergence rate of mirror descent and gradient descent in log scale. So the x-axis, the horizontal axis is just iteration, and the y-axis, this is suboptimality. Okay, and what you can see is that gradient descent, right, is the green line. It stagnates after 20-ish iterations, but mirror descent, it sort of continues to make progress rapidly. So yes, it's a theoretical difference, but really this theoretical difference is also borne out in practice.